So hello everyone, my name is Basil L. and I'm here with my colleague Moritz Blum. We are both from Bielefeld University and we will tell you today about our ontology related activities in the context of the DiProMag project. So we will talk about our ontology engineering methodology and about data integration. So I mentioned Otter already and Otter was mentioned before, so we will give a short introduction to Otter. We will tell you more about our Otter-centric ontology engineering methodology. We will give you some details and how we make use of the PMDco ontology and how we do this in practice. Next slide, please. All right, but before we go into those technical details about the ontology and about the methodology, let me first tell you about what kind of materials we are dealing with here. And we are dealing with magnetocaloric materials. These are specific alloys that have an interesting property. And the property is in a magnetic field, or with a magnetic field, we can control whether they absorb or release heat. So we can in principle develop cooling technologies, which are very interesting because these will be very energy efficient and environmentally friendly. And what we want to model here, we want to model the production of these materials, the characterization of these materials, and the prototypical applications of these materials, all in an ontology. And we beyond that also want to model the aims and ambitions of the researchers that carry out these experiments. Right, next slide, please. What we contribute to the platform Material Digital, so we create Otter templates. We model ontologies using Otter templates, and we use Otter template definitions and Otter template instances, and we can share this with the platform Material Digital and with the whole community. We have a demonstrator wiki, we have other demonstrators, we have developed workflows based on Pyrion and so on, and these can all be shared. There are a couple of links you can follow to read more about our project and to look at these demonstrators. Next slide, please. So as I said, we want to semantically represent, ontologically represent the production, the characterization, and the prototypical application of these magnetocaloric alloys. So on the right side, you see we have chemical elements. These need to be ontologically described. These will be assembled into composites, or we develop composites, and these will be semantically described. Then we have synthesis. So these materials are actually produced via an array of different processes and machines. So the machines need to be described, their configurations need to be described, then their samples will be created or stacks will be built. This will all be described, and then these samples will be analyzed and measurements results will be represented, or simulations will be carried out and their results will be represented. So that's the entire process chain that we digitize here. So let me tell you about the architecture. So on the left side of you see experiments. So we have a couple of different machines with which things are produced or things are measured. These things need to be configured. Then their measurement results. So on the top left, you see this is from the MP-MS3 machine, a data file. This is configuration and measurement results. This is the raw data we intake in our architecture. This is represented as JSON data and then sent to an electronic lab book where it can be queried and can be analyzed. It can be edited. Researchers can work with this data, and this data can then be fed back to the experiments. Or it can also be fed to our semantic media wiki, our semantic wiki, which makes use of Otter templates. So it contains Otter technology, it contains a library of Otter templates, which then help to transform this data into RDF triples, which can then be added to our knowledge graph. So we have a triples on the right side, so all the data can be digitized in the form of an RDF graph, in the form of a knowledge graph. This data as well can be used to create more experiments, or that can be used within experiments. And in semantic media wiki, it can also be, we can generate forms so that users, researchers can conveniently interact with this data. Next slide, please. So what is OTTR? Let me give you a very brief introduction into OTTR. So OTTR stands for Reasonable Ontology Templates. So it's like a macro mechanism to develop ontologies or to create RDF data. So this is a very simple template library you see on the left. A template library consists of a couple of template definitions. So here you see just one template definition about the pizza template. So imagine you want to describe a pizza, then maybe there are two things that you need to know. One thing is what's the name of the pizza, so the URI, the identifier, and maybe the label. And so these are the two parameters shown with a question mark here that you need for the template. And the modeling, the body of the template tells us that we generate an OTTR triple. We generate a triple where the name is the subject of the triple, RDF type is the predicate of the triple, and our class is the object of the triple. So what we say, whatever we pass as binding to the variable name will be part of this type class triple. So we define that that thing is of type class. Then we also define that it's a subclass of pizza, and the label also needs to somehow be attached via the RDFS label property to name. Subclass of here is a template that we call within the pizza template, so we can nest templates. And the subclass of template also needs to be described. It has two parameters, sub and super, for the subclass and the superclass, and we just use RDFS subclass of. Which is interesting here because we could also decide to use something else. Instead of RDFS subclass of, we could say maybe we want to use SCOS broader. So the decision to use subclass of is just given in this template. So if we want to change this design decision, we just need to change this template, and automatically the data would be regenerated with SCOS broader instead of RDFS subclass of. So on the left side, you have the template library, the template definition. But if we want to create real RDF data, we would instantiate those templates. So that's what you see on the right side. So we instantiate the pizza template with real values that are bound to those parameters. And we instantiate the pizza template with the URI margarita and the Italian label margarita. And the result of the instantiation you see below those three RDF triples. So the interesting thing is with these templates that they can be nested. So it's an abstraction mechanism. We can, in a modular fashion, develop ontologies or develop and generate RDF graphs. It's like a principle from software engineering that we have methods and those abstractions, and OTTR brings these benefits into ontology engineering. There are a couple of features that we have not shown in these simple examples. There are lists. OTTR can work with lists. OTTR can help with data type checking. There can be default values and optional parameters, and the graphs can be updated once we change design decisions. Next slide, please. So a couple of things I have mentioned already. So this OTTR allows us to create abstractions, which makes it easier for domain experts, for example, to understand what data is sent to some system to be represented in the knowledge graph. We can uniformly model things. So by instantiating templates, all those results of the instantiations look similar. So they are uniformly modeled. It is modular. We make use of the do not repeat yourself principle and so on. So these are the main benefits. Next slide, please. All right, then how does it work together with linked data, and where's the ontology really? How do we develop the ontology if we develop OTTR templates? So the main activity would be to develop the OTTR template library, which you see in the center. So this is where the ontology experts put most effort in creating this template library. These templates can also be represented as RDF data. So they are written in a specific user-friendly syntax called stotter, but they can be transformed into RDF and they can be linked data. So URIs and templates can be resolved over the web. Then once the data is there, we can use these templates to instantiate those templates, and these instantiations themselves can be represented as RDF and linked data again, but also via the OTTR engine called Lutra, we generate the RDF knowledge graph, we generate the ontology from those instances. And from the knowledge graph that we generate, from the ontology we generate, we can also derive the terms that are used in there. So that's the way we develop ontologies via Otter. And with this, I pass over to Moritz.
Thank you, Basil. So I start with presenting our methodology, so how we work and use Otter templates to develop the ontologies. And around this topic, we have published a paper at the workshop on ontology design and patterns this year. And the paper is called Insights from an Otter-centric Ontology Engineering Methodology. And this is what I present to you now, very briefly. But first, let me give you a short motivation why ontology engineering with Otter is useful and a good idea. Ontology engineering is, or there's still many challenges when developing large ontologies. For example, multiple design decisions must be made at the same time. For example, one has to determine the relevant information that should be modeled, and one has to find and identify suitable ontologies or design patterns for reuse. And as modularization showed benefits in large software development, ontology templates are something equivalent for ontology engineering. And they allow to construct large ontologies through template instantiations. The Otter language for ontology modeling patterns enables to build these ontologies by instantiating these templates, and this allows and provides some benefits. Basil already mentioned some, some benefits I want to highlight here. For example, the interaction on and working with the templates can hide the particularities of the ontological representation language from the domain experts, as the domain experts can work with us as ontology engineers on the level of templates instead of working with raw RDF data. Also, the templates enable the ontology engineers to separate the process of deciding what information to model from deciding about how to model the information, like, for example, which design patterns to use. And another benefit is that the templates help us to ensure modeling consistency. And for these reasons, we proposed this Otter-based, Otter-centric methodology that makes use of these benefits. And therefore, we are working in two opposite directions. So we are working bottom up and top down. This might sound a bit confusing. Let me explain this to you. So we're working bottom up as we begin with the existing data, instead of starting with higher level concepts. So we develop and start building our templates close to the raw data we have. And then we work top down as we first focus on which data to model, aka developing template headers, and then deciding about how to model the data, like how we develop and implement the body of the templates. So how the data is then represented in RDF. And by this, we can postpone some design decisions to a later stage when we have pre-structured the data already, and where it will be easier to model the data. And in in our project, we experienced yes, some these benefits, like we saw an enhanced communication with the domain experts through the auto templates, and we experienced a more flexible engineering process as the auto template encapsulate the modeling decisions. For example, we started implementing our ontology with EMO, and then we switched to PMDco, and this was quite easy as we had just to adjust some of the templates in this regard. And this is a list of steps and guidelines we followed to develop a template library and our ontology using auto templates. And then we follow a top-down refinement approach where we utilize the auto template headers as a starting point to develop the auto template bodies iteratively. Let me give you a brief overview. So some steps are quite similar to other methodologies. Some are very specific to Otter. So the first thing we did is to define the scope and screen the available data we have. Then, together with the domain experts, we designed the template headers, and then we asked the domain experts to verify these headers and to document them. Verification, for example, by putting in data and see if the data structure, how the parameters are match their workflows. Then we as ontology engineers started to design the template bodies, included axiomatic triples, and wrote the template documentation. Then we created the template library documentation, and in the end is the template instantiation and data integration. So this looks quite linear, but in reality, this is not so, or this flow isn't possible to follow that strict. So it looks more like this. So it's always or there are always back steps because you have to revisit some design decisions as when you enter a later stage because you were not aware of some things. So you go back, but that's natural for many methodologies. And this is what we also have experienced. And the outcome of the whole methodology, or the main outcome, is the template library that can then be used to create the ontology by instantiating the templates in the library. And as we don't have that much time today, I picked 3 different steps of this methodology. I would like to go into a bit more detail. And I would like to start with the design of template headers. And just as a reminder here, so a template header is just the template name and the list of parameters that are given to the template together with the types these parameters should have and whether they are optional or some default values. But I don't want to go into detail on that. I want to rather point out how we came up with these template signatures. And what we experienced is that the abstraction of these template headers, as they are just names and parameters mainly, is that the domain experts were able to follow or that we really were able to collaborate with the domain experts as they really understand what we try to model and how we model it. So they really contributed actively in the process. And when designing these template headers, we encountered some trade-offs that had to be made. For example, one can trade the complexity of templates versus the complexity of template relations. For example, you can create a template with many parameters that makes the update and practical use difficult. Or you implement or you split your data up into multiple templates, but then you get other difficulties like connecting these templates. So you somehow have to trade the complexity of template headers, so the number of parameters versus the number of relations between the templates. And the second trade-off I want to point out is that either you can have multiple similar templates. So you have for every specific situation, you have one template, or you have a few general templates that are more general and that cover multiple situations. These situation-specific templates might be more intuitive to use by domain experts, whereas it might be more difficult to ensure uniform modeling and finding the right templates. In general, one can say that many design decisions can or are similar to the entity relationship modeling. So there's no need to invent completely new concepts here. There are existing guidelines one can follow or that are very similar to what we have experienced. And as a result of this design of template headers step, we get an initial collection of template headers that can iteratively improved and when we do a step back from later steps. Here I would like to show you some templates. We have some template headers we have developed in DiProMag. What we have done is we were first looking at our workflows we have, and then we arrived. Then we were looking at the data, and then we derived the template parameters directly from this data. Then we came up with we decided to develop one template per processing step. For example, one template per material type, one template per synthesis method, and one template per measurement method. There we encountered the trade-off that splitting the data across multiple templates concerns the correlations and dependencies between data points. However, in order to avoid very large and very complex templates, as you can see on the right side, for example, the measurement magnetic properties modeling here is split into multiple templates. In general, on the right side, you can see how these templates are related and how they are connected, but I don't want to go into detail on that right now. The next step I would like to look at is the design of template bodies. And this is, for us, this was quite straightforward as the pre-structuring was already done through the template headers. And here we as ontology engineers started more or less with the template headers and the documentation of the template headers we got from the domain experts. because this already contained a lot of domain knowledge. For example, in the documentation, there were many domain-specific terms we were able to use. And we started by identifying suitable subtemplates. So, for example, which measurement values belong together, or are there like patterns across templates? For example, are there templates that always use the same parameters? These are potential candidates for subtemplates. And then we took these subtemplates and did a step back to the design of template headers and sit together with the domain experts and refined those templates. There are, of course, there are some difficulties where you can, where you have to do a step back. For example, if you're, if the structure or if the parameters and the separation into templates, if this does not match the ontologies you want to reuse, for example, PMDco, this might be the case sometimes. Then you also have to revisit some of your previous design decisions. Another difficulty is, of course, always modeling redundancy. So multiple templates implement similar design decisions, and this risks also inconsistencies. However, this can be avoided by introducing these subtemplates. Our experience is, as I've already mentioned very briefly in the beginning, that we started by using ammo. So I've an example around ammo here. So we started with ammo, and then it turned out that we had, or some of our measurements, for example, were split into multiple steps. So, and these steps, unfortunately, were across multiple templates. And then we have to introduce additional template parameters in order to reconnect this whole process. Or another experience is that a collection of similar physical experiments shares the same parameters, for example, about the environment. So many measurements collect the same data about the environment, and then we introduced new subtemplates we haven't thought about earlier. The last part of the methodology is the template library documentation that I want to mention here. And for the template library documentation, we first use Doctor. So Doctor already provides us a lot of tools. Doctor is a tool of Lutra, or in the Lutra engine, that provides a lot of features around Otter. For example, you can use Lutra to instantiate Otter templates when you provide the template library and template instances, or you can also use the Doctor feature where you generate the documentation pages for your template library. Doctor, for example, provides us a list of all templates and separates them into user-facing and subtemplates. So user-facing means these are templates where data is entered by users or by machines. And subtemplates are templates that are just called by other templates, so inside of other template bodies. This subtemplate structure is called template inclusion or template call hierarchy, and this is also provided by these Doctor tools. So this gives us already a good overview of how the template library is structured and how the templates are connected. Moreover, these documentation pages also provide us the documentation also and the templates also as RDF, and there are many more features that are already provided. The documentation then is a collection of websites. So you get overview pages, you get one page per template. And then through content negotiation, you can access the templates and the documentation. However, as Doctor already provides us a lot of tools in our project, we experienced that something rather practical was missing. And this is, we call this instantiation order. And the second thing that was missing were naming guidelines. To avoid mistakes when connecting template instances and to ensure consistency throughout the ontology, we experienced that the domain experts really appreciate and want to have and see benefits of having readable names. The names seem to be very important for the domain experts, the names of templates, of URIs. So we added some documentation about naming conventions there. So, however, unfortunately, the author does not support such naming convention, and also not the documentation does not, as it is, does not include and provide details about naming conventions. And the second thing that was missing is the instantiation order. And therefore, we developed workflows that describe how templates are connected and in which order templates would ideally be instantiated. In principle, it does not make any difference in which order you instantiate the templates. However, in order to follow existing workflows and to simplify the data integration process and to avoid some problems there, we developed we developed some ideal instantiation orders that can be followed. So these were the different steps I wanted to show. Now a few words about ontology design patterns. And we experienced that ontology design patterns really work great together with author templates. For example, you can have a template, an author template that represents a design pattern, and then you can use these design patterns through the author templates. And this brings the benefits of author features to ontology design patterns, like dealing with optional values and default parameters, or checking data type constraints. Of course, you can use ontology design patterns in any way you want in your templates. For example, you can also use multiple ontology design patterns in one template, or you can also split one or multiple ontology design patterns across templates. And I have the same figure for Shackle. So we are often asked about Shackle and Otter and the benefits and drawbacks of each other. However, we think that both could benefit from each other. For example, extending Otter templates with Shackle shapes in the template bodies can be really useful. For example, you can have one a Shackle constraint in one template, or you can have multiple, or you can even split Shackle constraints across multiple templates. And this figure we already saw when Basil presented. Shackle also fits into our Otter Shackle, and in this linked data figure we have. Together with the RDF graph of the ontology, the Shackle RDF is created through instantiating templates. And then an external Shekel validator can be applied to check if the ontology adheres to the Shekel shape restrictions. So next, I would like to look at our results. So our template library we created, and here you can see an overview of user-facing templates. So the templates that are used by machines or by users. And you can see that we have templates that follow our workflows. So we have template for composition, for example, DiProMag element and DiProMag composition. And then we have templates for the synthesis and samples for different synthesis methods and different materials, for example, arc melting for bulk materials or sputtering for thin films. And then we have templates for measurements of, for example, magnetic properties, thermal properties, and spectroscopy. And finally, we have templates to model goals and ambitions behind experiments. And now I would like to take a closer look at the measurement magnetic properties template and show that we are using the PMDco there. Here you can see some parts that were generated as a documentation, and the table shows the template signatures of the magnetic properties of the main magnetic properties measurement template. And this is a list of the parameters like the input sample or machine settings. I have to note that the measurement results are stored in a different template, and this is only mainly machine settings here. From in this table, we can see whether these which type these parameters have or should have, whether they are optional, whether there are blank nodes allowed, and if there is some default value. And below you can see a figure of the template inclusion hierarchy. For example, the measurement magnetic properties template uses different other templates down to the auto triple template. And inside the template bodies, we connect to the PMDco, and I would like to show this on the slide here. So we can see here a small part of the MPMS main template. The graphs, the auto template, and its sub templates would create. The intention here of the slide is to show that we incorporate the concepts object, process, and processing node. And I've used here some colors. For example, purple or our nodes in purple are classes of the PMDco, and in yellow I indicate parameters that are given by the template. And you can see here that we have in the center, the yellow node, measurement magnetic properties init characteristics mounting is the process, the main process node that has the type magnetic properties measuring process, which is a process, and it gets the input from or the input is a specimen, so an object, and it's executed by a certain machine that is a processing node. We also model processes according to the PMDco, and also we are following or we're using value objects and value scopes here. And now as the last part of the presentation, I would give some details, provide you some details about our semantic media wiki with the Otter extension we have developed. So we started our project with the semantic media wiki to organize information about our project and mainly about the ontology. And as we started developing Otter templates, we saw some benefits of representing them in the wiki. And therefore, we developed a semantic media wiki extension that allows to store templates, template definitions, and that allows us to instantiate Otter templates directly inside the wiki. And this allowed us to store and query the triples of the ontology directly in the wiki, while benefiting from other wiki features like administration, versioning of the pages and the discussion pages. And now we can look at how this works. Here you can see a template definition. Here is a template create composition. And this is a single wiki page. So you can create a wiki page and put a template definition in the Otter syntax, which is called stotter, on this page. And then this page works as an Otter template. Of course, you can also use our API to put template definitions into the wiki, but you can also do it by hand, by just using tags and then writing the stotter code. And once you have some template pages, you can directly benefit from wiki features like the collaboration and the versioning of wiki pages, and so on. Now you have the template, or you can put in your template library in the media wiki, and now you can also, or we also instantiate Otter templates inside the media wiki. And this can be done either by machines that use our API to input data for instantiations, or where we started was that we automatically generated forms for Otter templates that users can input their data. This is what we did to validate signatures of templates. So we asked our domain experts to input their data into the templates, and then we see whether these templates covered all the data and where are problems and what worked, of course, and so on. And these forms really helped the domain experts to instantiate templates, as they provide a really good user interface that is not only a single form, but also that provides the documentation and the types that is expected, and also some and also default values, and also some hints at some point. And on the right side here, you can see how then the instantiated template looks like. We also, of course, we generate the RDF, but this is not requested by the domain experts very often, so we don't show it here, but it exists inside the media wiki and can also be queried. And here you can see a query we made. So we used queries to ask for elements in our ontology and some of their properties, and then we generated such a table here. But what we can also do is to generate interactive visualizations. For example, here you can see a timeline when which element was added to the wiki. And yeah, this gives us many capabilities of working with the data. And of course, the RDF, or we have the RDF inside the wiki, but we are also able to export all RDF data and put it into a triple store and use it outside of the wiki. And now we slowly come to a conclusion. I first want to say about how we continue with our activities. So we have seen our architecture that is based on ELAB and Semantic Media Wiki, and we have integrated some experiments, but in the future we will do more integration, and we'll also use this architecture for managing our data. We will also, as we get more data, we will be able to do further analytical queries, and we plan to build more complex overview pages in our wiki. And of course, the more data we generate, the more knowledge we can get out of it, and we can do knowledge discovery that actually goes beyond reasoning. So we plan to do some ontology search in the vector space, and we plan to do hybrid knowledge graph completion and link prediction with graph neural networks that might also be time aware, as this turned out to be an interesting component. If you're interested, you can try our Semantic Media Wiki extension yourself. So we have published our extension, and we also provide Docker images with Semantic Media Wiki and our Otter extension. And the second thing is that we have not yet published our templates, but we already have a GitHub repository. So this is a link to the GitHub repository where we will publish our templates in the future. Yeah, Basil, I think you would like to do the summary.
All right, thanks. So I will do a quick summary. So at the beginning, I told you about magnetocaloric materials and why they're interesting. I mentioned the process chain that we digitized from elements via composition, synthesis, samples, and their properties. And I explained the architecture that we have from experiments with different measurement devices, the electronic lab book, Semantic Media Wiki, Otter, and the triple store at the end, how all of this is linked data. And then I also explained how Otter works in principle. Moritz then presented our Otter template-based ontology engineering methods. He presented 3 parts of this, and he explained he gave some examples of how those templates look. What they look like, how we make use of the PMDco ontology version 2.0, what we can do in Semantic Media Wiki, like creating queries and interactive visualizations. And with this, we are at the end, and we are happy to receive your questions and comments.